Okay, we are now into chapter 3, and everything that we were doing in chapter 1 and 2 was called propositional logic. Okay, and now we're going to move on from that, and we're going to start doing something that's called predicate logic. Okay. All right. Now, some of this stuff that we're going to be doing now, we actually mentioned way back in chapter 1. Okay, so don't let it confuse you that I'm going to be defining some things and using some words, and you might be thinking, well, wait a second, I thought we already did that. Okay, that's true. Don't let that confuse you. We have talked about some of this stuff before. Okay. All right, like for instance, open sentence. You already know what an open sentence is, but I'm going to define it again for you. Okay. I'm going to give it a new name now. I'm going to call them predicate. Okay. So even though we've seen the definition before, let's write it down. So a predicate or open sentence is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. And by the way, when we say values, that doesn't have to mean numbers. Okay, that could be other statements. Okay? Or it could be objects, like if I had the open sentence or the predicate, the car is blue. Okay? Then any car could be substituted into there. Like you could point to different cars. Okay, and that statement, the car is blue, will be true about some of those cars, and it'll be false about others of those cars. Each different car that you point to is called a value that you are substituting in for the variable. Okay? All right. Here's a new definition that we haven't seen before. So the word predicate is a new word, but we've seen that before. It's just that in the past we called them open sentences. Here's a new definition entirely. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. Okay. So let's do an example just to get an idea for this here, and we'll use numbers to make it simple. Okay, so let's write P of x, and that will stand for x squared is greater than x. Okay, and you can pick the domain for this. We're going to have the domain be the set of all real numbers. So in other words, I could plug in any real number into there. Okay? And some numbers will give me a true statement and some will give me a false statement. For instance, P of 2 is true. 2 squared is greater than 2. P of negative 1/2 is true. Negative 1/2 squared is greater than negative 1/2. P of positive 1/2 is false. 1/2 squared is not greater than 1/2. Okay? Now, if you asked this question, if you said, for which positive numbers is that true, then in that case you're saying that the domain is not all real numbers, but the domain in that case would just be the positive numbers. Okay? All right, new definition. If P of x is a predicate, and the variable x has domain, let's just call it D, the truth set of P of x is the set of all elements of D that make P of x true. That is the definition of truth set. Okay, and we write it like this. We say, listen to the words that I say as I'm writing. Okay, we say the set of x, that's an element of D, such that P of x. Okay? So for that example that we looked at earlier, down here, the truth set would be the set of all x in the real numbers such that x squared is greater than x. Okay? And you could think about what that would be. That would actually end up being the set of all real numbers except the closed interval from 0 to 1. Okay, so here's some examples. It says, let Q of n be the predicate n is a factor of 8. Okay, so Q of n is the predicate n is a factor of 8. Okay, it says, find the truth set if the domain of n is the set of all integers. So we're saying the domain of n is the set of all integers. Find the truth set of that predicate. So in other words, the set of all n in the integers such that n is a factor of 8. Okay, I'll write that down. The set of all n in the integers such that n is a factor of 8. So what would that be? That would include -8 and -4. You don't have to go in any particular order. -2, -1, 1, 2, 4, and 8. Those are all of the integers that are factors of 8, right? I don't think I missed any. Okay. Now, let's move on to quantifiers. And I believe we've actually seen these before also. So, let Q of x be a predicate. And let D be the domain of x. All right, the universal statement you've seen universal statements before in chapter 1. Okay, so I'm going to just write it out here. We write it like this. That symbol means for all. So for all x in D, comma, Q of x. Okay, what do I want to remind you about these? That is defined to be true if and only if Q of x is true for all x in D. Or if you prefer, we could say for every x in D. Okay? And then I'll put this in parentheses. If there is at least one x in D such that Q of x is false, then that statement is false. And that value of x is called a counterexample. So let's look at a couple of examples here. Okay, so let's suppose that D is the set containing 1, 2, 3, 4, 5. And let's look at this statement. For all x in D, comma, x squared is equal to or greater than x. So is that statement true or false? Well, in this case, there's only 5 elements of D, so we could just check them individually. That's called the method of exhaustion. You could just check. Is 1 squared equal to or greater than 1? Yes, it is. Is 2 squared equal to or greater than 2? Yes, it is. 3 squared equal to or greater than 3? Yes. And 4 squared is equal to or greater than 4, and 5 squared is equal to or greater than 5. So that Q of x right here is in fact true for every element of D. So the statement for all x in D, x squared is equal to or greater than x, is in fact a true statement. Okay? Now if I changed D to the set of all real numbers, okay, then let's just write for all x in the set of real numbers, x squared is equal to or greater than x. That is false, because I can name a bunch of real numbers for which this is not true. So that's a false statement. For instance, one number for which this is not true is the number 1/2. 1/2 squared is a fourth, which is not equal to or greater than 1/2. So the number 1/2 would be what we would call a counterexample. And to prove a universal statement false, all you need to do is find one counterexample. Okay? So as soon as I tell you that this is false for the number 1/2, then I can instantly say that this statement is a false statement. Okay? All right, now let's review existential statements. Okay. Let Q of x be a predicate and D the domain of x okay, an existential statement, which we've seen before in chapter 1. We write it like this: there exists an x in D such that Q of x. Okay, so that is defined to be true if and only if Q of x is true for at least one x in D. Okay, and then I'll put in parentheses that the existential statement is false if and only if Q of x is false for every x in D. Okay? Okay, and in the book, they give you lots of examples and practice on translating back and forth between words and symbols. Okay, so you should practice those. Now, let's look in particular at what we call universal conditional statements. That would look like this. For all x in the domain, comma, if P of x, then Q of x. So the book has been using just a one arrow like that for if then. Okay, if the domain is obvious, then sometimes people will leave off that part and just say for all x, P implies Q. Okay, now if that is in fact true for every x in the domain, so in other words, if that statement right there is a true statement, then we can write this. Whoops, I'm sorry, that's not right. Then we can write P of x implies, with a double arrow, Q of x. Okay, that just means that P of x implies Q of x is true for all x. Okay, and same thing with biconditional. So the book has been writing a biconditional with just one arrow like that. Okay, and maybe that biconditional is true for some values of x and it's false for other values of x. But if it is in fact true for all x in the domain of x, then in that case, if this is true, then you can shorten it by just writing this. Okay? Okay, so that's all for today. It's not too much because most of it we've seen before, so we're basically just reviewing. It's just that there's a couple of new words being used, that's all, but nothing here is actually new to you. Okay, but please do read the section 3.1 in the book. Like I said, they give lots of practice on translating back and forth between symbols and words, and you need to be able to do that. Translation back and forth. So please read those examples.